one for first year, and their semester ends ends. But there is for MTech, the classes are going on, sir.
Okay.
MTech and BTech second year, third year, and BTech final year.
Okay.
These are going on, that means parallel. But
Okay.
MTech is, but BTech's first year, it was started in January, and we are now planning to take their end sem. That means after 2 months, after 2 weeks, sir.
Yes, yes, sir. 21st March the exam.
21st. Okay, then next week, sir. Then next week.
Okay. Okay.
Yes.
Yeah. I think yes, because of the delay in the admissions of the first year students,
Yes,
they
sir.
are currently not aligned their semester with the regular students. That
Yes.
has been, I think, probably everywhere the similar situation exists.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Even we are not calling them to come here, and after
Okay.
that is completing first year.
Okay. Okay.
Yeah, then they will be here.
Okay.
Right now we are calling to first, that means second year student, BTech, third and final year, and MTech. They are coming from that means
Yeah.
last semester. Yeah.
Yeah. So in fact, all the students now have onboarded at IIT Delhi. All students.
That's great. That's great.
Yeah. So yesterday was the last day to onboard. So all have come. So now the teaching will continue in the online mode, but all the exams, etc., they have to be held in the offline mode.
That is great, sir. That is great. Otherwise, we are not able to justify their grade even.
Yeah, that's right.
That is the big problem.
Yes. So next semester it will be full. Everything will be offline.
Right, sir. Right, sir. Right, sir. So even sir here we are taking classes for MTech second year or MTech first year. We are taking classes offline mode, and we are planning. That means it is in schedule that from next that means week, that means from 21st March, we are taking all the classes offline mode except BTech first year.
Okay, that's nice.
Yes, sir. Yes, sir. Still people are joining. Yes, sir. Dr. Ashok, sir, still people are joining.
Yes, 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 sir. Actually, I am admitting also, so people are joining.
Right. Some sound is coming. It's still people are joining.
So 40 participants has joined, Dr. Manoj, sir.
Right, sir. Right, sir. Right, sir. Yes, Farooq.
Manoj, sir.
Ji, sir.
I think we can start.
Please, sir.
So, okay. So dear participants, welcome you all. So today in between we have Professor S.V. Modasarji. He is professor in IIT Delhi. So welcome, sir, in this short-term course. So participants, the search interest of search area of Professor S.V. Modasarji is finite element model updating, vibration, acoustics, active noise control, active vibration control, and etc. So it is a great thing to all of us that the person who is definitely he's in IIT, but he has a great knowledge in different areas. So we can take his advantage in terms of his knowledge and learn new things from him. So it is a great opportunity to all of us. So as I have already said during the start of this FDP, that we most of the time we don't get any opportunity to go IITs and study there. So these type of online modes gives us opportunity to interact with the persons who is in IITs and great professors there. So please during the interaction or during the question answer section, please ask your queries, your doubts from Professor S.V. Modasarji, so that you can clear all your doubts and you can use that knowledge in your future work. So Professor S.V. Modasarji, so welcome to you in so.
It's our great, I should say that pleasure to Professor is here. Dear participants, take great advantage. I suggest everyone, please make it very interactive. Whenever you need any query, please ask.
Yeah.
We have a great personality in this particular field, model analysis, especially experimental model analysis. I would say that is one of the toughest area to understand the vibration and its response. Sir, please, sir. Welcome, sir.
Thank you. Thank you, Dr. Ashok Kumar, for introducing me and for your kind words, as well as Dr. Manoj Kumar for the kind words you used.
Thank you.
And so, namaskar, all the participants. Share my screen to start with.
Hanji sir, you kindly.
I'm just clicking that vertical arrow. Just a minute. Screen. So I have shared it. So let me know once it is visible to you. So I have shared my screen.
Yes, it is visible, sir. Yes, it is visible.
Okay. So you can see the first slide, I suppose.
Yes, sir. Yes. Sir.
Okay. Now I will switch over to the PowerPoint mode. Let me do that. I hope now the slide is visible in the PowerPoint mode, right?
Yes, sir. Yes, sir.
Oh, thank you so much. So I'm very happy to be here again. Last time also we had a lecture on this topic, and the title of this lecture is Experimental Modal Analysis. Before I start, I would simply say that as Dr. Manoj Kumar also said, that feel free to ask questions, okay? And you can interrupt me at any point of time, okay? Just raise your voice, because I am not able to see anything other than my slide, okay? So I can't see anybody, any faces or participants, raising hand, etc. So if you have any question, just interrupt me by switching your microphone on and raising the question, okay? और ये भी कह सकता हूं मैं कि आपको जैसे भी आपको कन्वीनियंट लगता हो वैसा क्वेश्चन पूछ सकते हैं, चाहे आप इंग्लिश में पूछें, हिंदी में पूछें, ठीक है? तो आपको मतलब उसमें हेजिटेशन की रखने की आवश्यकता नहीं, आपको जिसमें भी कन्वीनियंस हो उसमें आप क्वेश्चन पूछ सकते हैं. So let me go to the next slide. So this is also Dr. Ashok Kumar. How much time we have?
Sir, it is up to you. We have no problem in that. There is no time limit, but 1 hour or maybe 1.5 hours, it is. I think it is sufficient, sir.
Absolutely, I think that should be enough to complete a lecture. But in case you feel that you need to stop at some point of time, just give me a signal for that. Okay?
Sure, sir. Definitely, sir. Sure, sir.
Yeah. So this is the outline of my lecture. So I have divided this lecture answering some fundamental questions So we start with what is modal analysis. Then how modal analysis is carried out. What is the need of what is the need of experimental modal analysis? Experimental modal analysis is also known by another term called modal testing. Then what is modal testing or experimental modal analysis? What is the basis of modal testing? How modal testing is done? And what are the applications of modal testing in practice? So when I worked out all these slides, my idea was to give you a very broad but complete overview of the whole area, starting from the fundamental equations, going up to the level where one can understand what is modal testing and how modal testing is done, and then also looking at some of the important applications where the results of modal testing can be used. So I think the idea is that not only you should get some bit understanding of the fundamentals, but at the same time you must know the overall scope and application and the possible application of this area. That is the idea behind this lecture. So we start with our first question, that what is modal analysis? So before we answer that question, there is a bit of theory, background theory that probably may help us to understand that. So I believe some of you and many of you probably must have done a course in vibration engineering or mechanical vibrations, right? So what is the term? We say dynamic analysis or vibration analysis. So dynamic analysis or vibration analysis refers to study of response of structures to dynamic forces. The forces which may arise in practice on any structure or system, mechanical system or any physical system, the forces may be either static forces or dynamic forces. Static force stays constant with time. It does not change with time. Okay, while the dynamic force is a force which changes with time, and that is why it is called dynamic. For example, the force experienced by a structure due to its own weight is a static force because it is due to gravity, and gravitational force stays constant with time, right? But other forces, for example, let us go to next slide to look at the forces, dynamic forces. So different dynamic forces, which may act on structures could be like due to rotating unbalance. For example, many machines have rotating parts like a motor or an ice engine or a pump or a centrifugal compressor and so on, or fans. They have rotating parts like blades, etc. So what happens? There will be always some amount of unbalance present because the center of gravity of the fan or the rotating body or rotating member may not be exactly aligned with the axis of rotation. And because of the difference between these 2 points or these 2 axes, there would be a centrifugal force that would come into play. And that would eventually be transferred to the supporting structure through bearings. And therefore, the supporting structure would be acted upon by unbalanced forces. And this force is of rotating nature because the body is rotating, it would be of rotating nature. And therefore, if you look at, let us say, force in the vertical direction, that force will be continuously varying because the force, centrifugal force is rotating and its component would continuously change. Similarly, there could be reciprocating unbalance. The reciprocating masses, for example, in an ice engine, the piston mass, it is a reciprocating part, and some amount of the mass of the connecting rod, they basically make up the reciprocating mass. And then this particular reciprocating mass in general cannot be easily completely balanced. And therefore, that also, is then finally, transferred to the supporting structure through bearings. And that also, therefore, is an unbalanced force. Similarly, you can have impacts. For example, a forging press in workshop, it applies an impact on the, on a sheet of metal in order to create some hole or some other, object, right? And therefore, those impact forces again would shake the foundation and would, eventually vibrate other machines which are nearby. Aerodynamic forces, when a car moves, for example, on the road, there is a aerodynamic drag, and because of the turbulence and the boundary layer effects, there is a drag and of aerodynamic forces acting on the vehicle, and they again are dynamic in nature because they don't stay constant with time. They depend on the wind velocity, they depend on the other environmental conditions. Fluid flow, for example, a ship moving in the water is exerted upon by waves, right? And then again, the viscous forces due to fluid, they all act on the structure, on the body which is moving. And that again is the dynamic force. Waves also already example I have given to you. Even combustion, which occurs in the IC engine, what happens? It's a impulsive moment. Suddenly, when there is at the end of the compression stroke, there is a combustion in the in the cylinder, right? And then what happens? There is a sudden rise of pressure, and that sudden rise of pressure, what does it do? It is going to again act on the adjoining structure, walls of the cylinder everywhere, and then some force would be transmitted to the surrounding the housing or the body through bearings. So that also is a dynamic force. Okay, so you can see these are some of the forces. There may be some other sources of dynamic forces on structures. And what is going to happen? All these dynamic forces are going to, because they are varying with time, what do? They lead to oscillatory displacements. Because a static force causes a static deflection. But if the force is changing, the direction and the magnitude of the force is changing, then it's going to cause a deflection which is also changing with time. And this changing displacement is called oscillatory displacement. And oscillatory displacement is nothing but vibration, right? So any physical system subjected to dynamic forces would undergo vibrations. And that may be a system in mechanical engineering or civil engineering, like a building or a bridge, or in other areas, for example, a computer, computer desktop system, it has a fan, and a fan, you can see, it generates vibrations, right? It generates, the acoustic waves, and all that thing also causes the computer system to vibrate. Or a disk drive in the computer, when it, the disk rotates, when we access any data, then what does it do? Again, there will be some dynamic forces which will come into play. So the point is that any physical system subjected to oscillatory forces is going to, will undergo vibrations. So vibration is basically mechanical phenomena, right? Where the points move with about the equilibrium position, right? But again, just to be cautious that these oscillations, they are not only restricted to physical, the mechanical system. You can have oscillations in acoustic systems also. For example, I would talk about some slides later that what are the oscillations in an acoustic system. Electrical systems or electrical circuits also have oscillations, because if you have AC voltage, that AC voltage may cause vibration in electrical circuit, right? Okay, so that is also means oscillations are there. But of course, being mechanical engineers, we are more concerned with the oscillations in physical systems, right? Which basically is the movement of a body about an equilibrium position. That is the oscillation we are concerned with. So this is just gives you a brief idea about the different types of vibratory motions. For example, you can have, I think, let me pull out the pointer. Yeah. So I hope pointer is visible to you.
Yes, sir.
Yes.
Okay. Thank you. So you can see, for example, electric motor. It rotates at a certain RPM, and then because of some unbalance, there will always be an rotating unbalanced force, and it would cause, because generally the unbalanced force, it would be dominant, create dominant vibration at the frequency of rotation, right? And that's why it is generally will be an harmonic force. It will be a harmonic force, and the resulting vibration is an harmonic vibration. And therefore, if you plot on a time axis x versus t, you would see a curve like this, a sine wave. It's called harmonic vibration. But if you, let us say, if you have a diesel engine, and if you put your accelerometer on the surface of the diesel engine and measure that vibration, and then let us say try to see its waveform, it is likely to look something like this, shown by green color, green line, right? This vibration is generally not harmonic. It has got multiple harmonic harmonics. I would say the fundamental there would be higher harmonics, which means the fundamental rotatory component, there will be harmonics of that fundamental rotatory component, right? So if the RPM is n, you will have 2n, 3n, 4n, those frequencies also would be present in the vibration. And that is why the waveform doesn't look like a sine wave, but it looks like a summation of many sine waves, right? So it's called periodic vibration. A car, for example, moving over a speed breaker, we all have experienced this, that we momentarily experience a kind of an upward, jerk, right? So So, and then when the car has moved over and has gone past the speed breaker, then again we feel, there is no motion in the upward direction, right? So if you plot again the vibration of the, let us say, seat of the passenger, and it may look something like this. So where the vibration, suddenly are initiated at some point of time, and then they gradually, decay. It's called transient vibration. If a cyclist is moving on a rough road, the vibrations experienced by the cyclist, if you plot as a function of time, it may show a very irregular change and variation. And therefore, you can't associate or allocate any law by which these vibrations or displacements are changing. And therefore, we call them as random, right? We say that, okay, if it's, we cannot associate or assign any law to it, it is basically a random change. And that's why these vibrations are random. So therefore, you may have harmonic vibrations or periodic vibrations or transient vibrations or random vibrations. So these are basically the broad categories of vibratory motions. So what are the consequences of vibration? If vibrations are there, often these vibrations are not desirable. In most cases, these vibrations are not desirable simply because vibration, what does it do? It causes an oscillatory displacement. So it means there will be the strains which occur, right? And the stresses which occur because of that, they all also will be oscillatory. And oscillatory stresses, what they cause? Fatigue. They cause fatigue. Okay. So therefore, therefore, the one important consequence of vibration is fatigue of the material. So it is subjected to a continuously changing strains and stresses with time, and it causes fatigue. And fatigue, that fatigue, the fatigue life is less than the life without fatigue, right? So if a machine component is there, if there is no fatigue, it can last for a very long time. But if it is subjected to fatigue, which means the oscillatory loads, its life will be less, right? And therefore, that is one consequence of vibration, that it causes fatigue and reduction in the life. Then vibration also causes noise. For example, if a machine is vibrating, you often hear some noise coming out of it, right? For example, if fan is switched on, then you hear noise. So any machine, a motor is running, you immediately hear something, right? So that is a byproduct of any mechanical vibration, that it also causes noise or sound waves. It is called discomfort. We know that called discomfort. So I think probably you can easily understand this point. So all systems we see around, nearly all of them have vibrations, like automotive vehicles, aircraft, ships, machine tools, industry equipment, consumer goods, all other engineering structures like a bridge or a building, right, or dam, all they undergo vibrations. But there are some cases where vibration might be desirable, where we actually intentionally produce vibration. For example, in musical instruments, for example, a guitar, especially the acoustic guitar, when we pluck a string of an acoustic guitar, what does it do? That guitar string vibrates. The vibration of the string are transferred to the wooden box. You might have seen that big wooden box, and that is hollow, right? So the vibrations are transmitted to the the wooden box of the guitar, right? And then the air medium inside the box, it is set into motion and vibration. Okay. Acoustic waves, and then through a small opening in that box, the acoustic waves come out and we hear something, correct? So you can see by inducing vibration of the string, we are generating music. So here the vibration is intentionally produced, right? So there are other musical instruments also we do that. In tabla, for example, what do? You strike, you play on the tabla, and the top surface of the tabla is like a circular membrane, right? And that membrane, it's undergoing vibration. And it is producing, and what does it do? Because air is in contact with the that surface of the tabla, that air is set into vibration, and that air vibration motion is then communicated to our ears, and we interpret that as the sound. So therefore, and then there are vibrating conveyors where the conveyor is set into vibration, so that the material, typically a granular material which is lying on the top surface of the conveyor, that is gradually moved forward, right? So I think there are some applications where vibration is intentionally used. So then with this background, now we are in a position to understand and address the fundamental question that what is modal analysis? So, every structure which vibrates, right, every physical system which vibrates has natural modes of vibration, right? It has some natural modes in which it can vibrate. Okay, so when you disturb a system, in under free condition, right? You disturb a system, you just disturb it and leave it, then it will vibrate with some fixed natural modes. It will not vibrate arbitrarily. Okay, so if there is any physical system, you hit it. For example, this desk is there. If I hit it like this, then because I'm just disturbing it and then leaving it, so now this desk or any other physical system, it would vibrate in some fixed natural modes of vibration. In fixed way, there are some fixed patterns of vibration which it can acquire, and those patterns of vibration are called natural modes of vibration. So mode analysis is a subject in which we study these natural modes of vibration, right? That what are the natural modes, and we also want to know that how the dynamic response, right, is generated through these modes. How do the dynamic response of a structure subjected to dynamic forces is generated when because of these natural modes of vibration. So these are the two objectives of mode analysis, two very broad objectives. That and most fundamental, that that what are the modes of vibration? That is one thing we want to understand. Second thing we want to do is use these natural modes of vibration to study the dynamic response. These are the two principal aims of mode analysis. And what are modes of vibration? The modes are described by their natural frequencies, mode shapes, and damping factors. These are the three quantities which describe a mode of vibration. What is the frequency of vibration? Well, what is the deflection pattern or deformation pattern acquired by that system when it is vibrating at that frequency, natural frequency? That is called mode shape. And then every mode has a property, to decay, to dissipate energy, right, when vibrating freely. Then that the way it dissipates, the rate at which it dissipates energy is quantified by using a factor called damping factor. So collectively, this information is referred as modal of the structure, right? So what is modal? It is the description of natural modes of vibration using natural frequencies, mode shapes, and damping factors. So therefore, modal analysis is also sometimes referred as process of determining a modal of the structure. You are trying to identify what is the modal, which basically means identifying the description or the characteristics of natural modes of vibration. So I hope that you now probably can understand that what is modal analysis and what do you do in it, right? But then the question arises that why modes of vibration need to be studied? Why should we study the modes of vibration? Because we see that the most noise and vibration problems are related to resonance phenomena. In practice, when we see that, okay, there is some problem. For example, in a car, we see that, okay, there is, in a passenger vehicle, we, often see that, okay, there is a lot of noise inside the car. So one of the principal reasons for that could be resonance, acoustic resonance in this case. It could also be mechanical resonance. If a body is resonating because of the engine forces, then it will release more noise into the cavity. Or a machine, for example, a machine is generating a lot of noise. So maybe that the casing or the cover which is there on the top of the machine is being subjected to forces which is causing that casing to vibrate in its natural mode, and that is causing a lot of radiation of noise, right? So therefore, there are many examples where resonance is responsible for vibration and noise. So that is why we should study modes of vibration, because when does resonance occur? Resonance occurs when the frequency of the dynamic forces which are acting, or dynamic force which is acting, coincides with one of the natural frequencies of the system. So there is a dynamic force and it has certain frequency of motion, a frequency of variation. If that frequency coincides with one of the natural frequencies of the system, then resonance occurs. And at resonance, the vibration level becomes is relatively much higher as compared to a condition when resonance is not there. And that is why we should try to avoid resonance, right? Because resonance indirectly is going to lead to a lot of vibrations and all the consequences which occur because of the vibration. So this is one important reason for knowing what are the natural frequencies and studying modes of vibration. But there is another important reason, and that reason is that these modes of vibration, they form the basis of a mathematical model of the structure. So using these modes of vibration, we can describe, or we can generate, or we can construct a model of the structure, right? just like finite element model, right? You must have studied in earlier lectures. Finite element model, you can study the response of a system to inputs, using finite element model. So through modal analysis or through modal testing also, we can generate an alternative definition of model. We can generate an alternative form of the model, and that is in the form of modal model. Okay. Okay, so let us go to next slide. So I think now we have explained that what is modal analysis. Now we are going to take up the next question, that how modal analysis is carried out. How do you do modal analysis? Okay. Now there are two approaches to modal analysis. One is called analytical modal analysis, and another is called experimental modal analysis or modal testing, right? So in order to understand that what is experimental modal analysis, it is necessary to first understand what is analytical modal analysis, because that understanding will lay the foundation for developing the principles of experimental modal analysis. And that is why we need to first understand what is analytical modal analysis, and that is what we will do first. What is analytical modal analysis? So this is the problem I often take, to explain, that what is a vibratory system and models and so on, because it's a very simple system, and it is often seen in industry that, we have, for example, a prime mover or a source of power like a motor. It is to be supported, and there may be some bracket, etc., that might be used to support this, thing. You can see this is the bracket. It's like a cantilever kind of structure, and then there is a motor mounted at the tip of the cantilever, right? Now when this motor operates, then as I explained earlier, it is going to generate dynamic force. So you will have a force in this direction acting in the vertical direction. Of course, there will also be a force in the horizontal direction. But if you focus our attention on the vertical direction, then bracket is going to vibrate like a cantilever beam, right? And then to study this phenomena, that how does this motor causes vibration of this cantilever, one approach is analytical modal analysis, in which we will first build a model of this system, right? And that's why we need a mathematical model. Now, how to build this mathematical model? Let us go to next slide. So there could be the simplest approach is to build a lump parameter model, mathematical model. And because we are interested in studying the vibration of this system because of the forces generated by the motor, three properties need to be taken into account to study this physical phenomena, of vibration, right? One is inertia, because mass is important. Mass affects vibration. Elasticity, which is basically the stiffness of the system, that also affects vibration. And another is the damping, the natural ability of the system to dissipate inertia, that is called damping. So any mechanism which is there in this system which may dissipate energy is quantified as damping. It could be friction forces, it could be aerodynamic drag, it could be a hysteresis effect inside the material, it could be viscous friction that might be present. So whatever sources are there, all of them we represent through a single term called damping, right? And the simplest model we can make is a single degree of freedom model, in which we are interested only in one coordinate of motion, that what is the vertical displacement here, let us say. So then you have just 1 degree of freedom you are concerned with, and therefore you are making a single degree of freedom model. So we can have an undamped model where we ignore modeling of damping, or we can have a damped model where we also take into account damping, right? So this is called a single degree of freedom model, and I think you must have studied this earlier. And then a better way to model this, or if you want a more accurate model, more accurate prediction, then you may have to go for multi-degree of freedom model. For example, for a car, because you can see the tire may have some stiffness, right? Then your suspension may have some stiffness. So therefore, if you just represent it by single degree of freedom model, the predictions may not be accurate enough. So therefore, we go for a 2 degree of freedom model. So therefore, what do? We model the stiffness of the tire and the damping through these 2 springs and dampers, and then we have this mass of the axle and the tire being modeled as this lump mass, and then we have the suspension stiffness and the damping, right, modeled through this spring and dashboard, and then we have the mass of the body of the car plus the mass of the engine and all the bodies which are being supported by the body of the car. They are all being lumped in the form of this second mass, and therefore the vertical displacement of these 2 masses, they represent 2 degrees of freedom, right, which we are trying to study here, and this makes this model a 2 degree of freedom model. And then if the car is moving on a rough road, so we can now study that how this rough road causes the vertical vibration of these two masses. A further way, for example, now if you want to study that how the noise is radiated inside the car, let us suppose, right? Then the body of the car, right? This body is flexible. You know that it is made of very thin sheets, and then it is flexible. Because of the flexibility, it has its own modes of vibration. And then those modes of vibration, what do? They radiate sound energy into the cavity, into the cabin of the car. So if you want to study that, then this 2 degree of freedom model will not be enough, because it doesn't allow us to study that how the flexible body of the car is going to vibrate. And therefore, if the objective is if the objective to study the sound developed inside the car, then probably the better model would be a finite element model through which we can model this body of the car, and then we can apply the forces on this body which are coming through engine and through a road, etc., or aerodynamic forces. We can apply on this model and then study that what is the sound that is generated inside the car. So therefore, depending upon the purpose of the study, the choice of the model has to be made. Sometimes a single degree of freedom model may be enough. Then we should not unnecessarily go for a very high sophisticated model. But there could be applications where that simple model may not be enough to answer our questions. And in those cases, we may have to go for more sophisticated models, right? So that is why one should not always just simply say and jump on the wagon, gun and say that, okay, I'm going to go for a finite model, because that is probably the best I can do. I have very good software. No, you have to, as an engineer, you have to think, what is the question I want to address? What is the result I want to get? What is the objective of my study for which I want to make the model? Based on that objective, then one takes a decision, what kind of model would be enough? And according to that, the model should be built. Okay? So, so let us now try to understand that if once you have a model, this model is in the form of mathematically, whether it's a single degree of multi-degree of freedom model or a finite model, all those models finally in the form of equations, they look alike. All of them will be described by 3 matrices. One is the mass matrix, stiffness matrix, and damping matrix. Although in this case, I have taken the undamped system, so there is no damping matrix. And then you can write down the equations mx double dot plus kx equal to 0, right? And then if there is because we are trying to study the natural modes. Natural modes are the modes when any system vibrates under free condition. And that's why here we are not including any forces. You can see the right hand side is 0 because we want to study natural modes. And then we see that because the vibration is going to be at certain frequency omega and the natural condition at certain natural frequency omega. And then when we substitute this thing here, we end up with this problem, which is called an eigenvalue problem. K minus omega square m into x is equal to 0. This is a very important problem. In mathematics, you must have studied eigenvalue problem, right? So anywhere we have this kind of equation, you can see it's not a set of linear equations. There is no right hand term here, right? In case of linear equations, we have a right hand constant term here, but in eigenvalue problem we have 0 here. So it's an eigenvalue problem. So when this problem is solved, we get eigenvalues and eigenvectors. So when you solve this eigenvalue problem, because the size of the matrices is n by n here, if the n is the degree of freedom of the model, then we get n eigenvalues. It is typically written in the form of matrix of eigenvalues. All diagonal terms, they are the eigenvalues. And natural frequency is square root of the eigenvalues, right? So if I have an eigenvalue omega 1 square, the natural frequency is omega 1 radian per second. If I want it in hertz, I should divide it by 2 pi. So omega 1 upon 2 pi is the natural frequency in hertz. So in this way, I by solving this eigenvalue problem, I come to know the natural frequencies. Then I have matrix of eigenvectors. For each eigenvalue, you can see for this eigenvalue, I have this column. This is the eigenvector corresponding to this eigenvalue. This is the eigenvector corresponding to this eigenvalue. This is the nth eigenvector corresponding to nth eigenvalue, right? So this eigenvector is nothing but motion. It tells you that what is the relative displacement profile of the system when that system is vibrating in the corresponding natural frequency. So if a system is vibrating at let us say the first natural frequency at omega 1, then the relative displacement profile of different degrees of freedom will be described by this first eigenvector and so on. So I think these are the fundamental properties of the system. So eigenvalues and eigenvectors, or natural frequency and mode shapes, they are the fundamental characteristics of the system. They don't depend on the input, what force we are applying. It simply depends on the system. So that is one objective of analytical model analysis or model analysis, that to find eigenvalues, eigenvectors, or natural frequency mode shapes, right? And generally, in analytical model analysis, we often start with undamped problems by ignoring damping, simply because it is not easy, or rather I would say it is the information is not there to model damping in models. So that is why often the software packages, finite element software packages, what do? They model the mass and stiffness matrix. But for damping matrix, you can take a proportional damping matrix. But the problem is that what proportionality factors you would take. So based on a pure finite element model, okay, with no other information available, it is actually not possible to model damping. We don't know what is the damping, and that is why through finite element model you cannot model damping. The only way you can model damping through infinite element model is that we estimate damping factors from experiment like modal testing, and then try to generate or estimate some proportionality factors, and then incorporate those proportionality constants in a finite element model, right? So therefore, the finite element model, softwares, they would allow you to model damping, but then the question would be that what proportionality factors do you take if it is proportional damping? That is the problem. So therefore, they ultimately have to come from experiment. So therefore, you can see the second objective of analytical model analysis is that how do you study the dynamic response in terms of modes of vibration? And for that purpose, what do? You basically do a modal transformation. X is equal to phi y. Okay, x is equal to phi y. So here x is the physical displacement and y is the modal displacement, and phi is the matrix of eigenvectors. So basically, you are saying that each physical vector consists of response in each mode of vibration. So you can see phi 1 into yr1, phi 2 into yr2. What is phi 1? Phi 1 is first eigenvector. Yr1 is a scalar, which says that how much of the first eigenvector is present in the total physical displacement. Second eigenvector says that yr2, which is the modal response in mode 2, it tells you that how much of the second eigenvector is present in the total physical displacement. This has been shown through this figure. You can see this on the left hand side. This is the way, let us say, cantilever beam is vibrating. This is the response, dynamic response, right? Dynamic deflection at some point of time, at some instant, to dynamic forces. This is something visible to us. But through modal analysis, we can break down this total response in terms of response in different modes of vibration. So this is the first mode of vibration, and this is the response in the first mode, right? So this is the plot of this complete term. Second, this plot is the plot of the second term, and so on. So you can see these are all the natural, the modal responses in different modes. And if you sum these modal responses total by multiplying them by the eigenvectors, you get a complete physical vector of response. So this is the second aim of analytical model analysis, to study response in terms of modes. Okay. Now, so how do you determine? So I think I will quickly go through this slide that if now we have a force F, how you analytically study the modal response. So I think we again do this transformation. We post and pre-multiply by phi and phi transpose. We get modal. The equations get decoupled. These are coupled equations. These are decoupled equations, and then we get the matrix of modal responses here, vector of modal responses here, right? Y is equal to kr minus omega r square mr inverse fr. So these kr and mr are the modal stiffness and modal mass. Right, so modal response can be described by a single degree of freedom vibration in each mode of vibration, and each single degree of modal response is characterized by a modal stiffness and modal mass. Right, so this is basically the modal response. So therefore, what do you do in effective analytical model analysis? That we have a spatial model. A model which is in terms of matrices, mass matrix, stiffness matrix, and damping matrix. This description of a structure or a system is called spatial model. Okay, a spatial model means description in physical coordinates through mass, stiffness, and damping matrix. And then through eigenvalue problem, we convert it into a modal description or modal model. And this description is in terms of natural frequency, mode shapes, and damping factors. Okay, and these two descriptions are equivalent descriptions. Theoretically speaking, okay, these two descriptions are completely equivalent descriptions, and theoretically, of course, they are true in all respects. That is true, but for analytical purposes, the model, a complete model might be available, but in experiment, complete model may not be available. So therefore, in theory, it is possible to convert a model to a spatial model, and spatial model to a model model. It is possible, right? So I think this is the basically one of the aims of model analysis, that we obtain model from a spatial model. So now so once we have now understood that analytical model analysis is possible, we can develop a mathematical model of the structure or a system through either a lump parameter model approach or a degree of freedom model approach or a finite element approach. We can develop a model of the mathematical model of the structure, and then we can perform model analysis. We can study the modes of the modes of the vibration. We can also study the modal response, etc. But then, if that can be done, what is the need of model testing, right? Why we need model testing or experimental analysis? So one of the important objectives of using the information we obtain from model testing is validation of analytical models. Because if we have made a model, what is the accuracy of model and dynamic predictions or analysis done using analytical model? That is the question. How do you answer that question? If you made a model, and if I ask you, is this model accurate? Is it correct? How do you answer this question? There is no way. The only way to check this or answer this question is if we have a reference data available with us, or if we have a data which we can say is accurate. We can compare results of an analytical model with that data, and then we can say that our analytical model is good enough or not. That is the only way. Without having any other independent source of information, you will not be able to judge the accuracy of an analytical model. Whatever is the source of that model, analytical model is, whether it is lump parameter approach or a finite element approach or any other approach. Whatever analytical model you make, the only way to check whether that model is good enough or not is to compare it with experimental data. That's the only way. There's no other way. And therefore, model testing provides a procedure or a method to determine the dynamic characteristics, natural frequency, motions, and damping factors through experimental testing, right? So that is one important application of model testing, right? In order to validate, check accuracy of numerical models. And of course, as I explained earlier, that once you have model available, because model testing directly gives you a model. It does not follow the analytical route, right? It directly gives you a model. So because model itself is a model of the system, so that model itself can be used for predicting the dynamic response. You don't need anything else. You can use a model to predict the dynamic response to any dynamic forces. Okay, and so therefore, model testing provides an independent model, completely, the alternative form of model it provides, and that which has in its own right can be used to study the dynamic response. You don't need anything else. Okay, and you don't need to validate that model because you are directly acquiring it through experiment. And if all precautions have been taken to ensure that there are no errors in the experiment, then that model can be assumed to be a good model of the system, and hence we can use it independently. Okay, so that is the second important reason for studying model testing. So just give me a couple of seconds. I will try to have some water. Okay, so now we go to next question. What is model testing? I think maybe because it's 10:42 and I have many more slides. So what I would do is I would try to further go up, and if you have any questions, please feel free to raise. Right. So model testing is an experimental method to find natural frequency, mode shapes, and damping factors of a structure. Or in nutshell, we can say that we are trying to obtain a model of the structure, right? So these two terms are very important, modal and model. MODAL is modal, and that refers to relationship with modes of vibration. Modal refers to modes of vibration, while model refers to a model of the system. It could be a finite model or spatial model or a response model. It's a model of the system. It's a mathematical model of the structure. So these two terms you must be very careful in using and pronouncing them. Otherwise, they have a different, completely different meaning. Modal and model. Modal, model. What is the basis of modal testing? So, you know, the dynamics of a structure can be described through three different types of models. One is spatial model, which you have studied. Analytical model is a spatial model. Description in terms of mass, differential, and damping matrix. Modal model also we have studied, which is description in terms of, you know, eigenvalues, eigenvectors, and damping factors, or natural frequency, mode shapes, and damping factors. Or third model is response model. What is response model? Understanding of this is important for understanding modal testing. That what is response model? Coming back to the equation we studied and looked at on one of the previous slides, the modal response, right? So this is the modal response Y is equal to this quantity. And you know, if you use mass normalized modes, if you normalize the modes with respect to the mass matrix, then the modal mass matrix is unity. Kr, the modal stiffness matrix is diagonal matrix of omega r square. And you know, finally we end up with this equation. So what we do, we find modal response and substitute back in this equation, the modal transformation, and then we get the physical, you know, response in the physical coordinates x. And if you carefully look at the right hand side of this equation, it has got two parts. The rightmost part is force vector F, and the coefficient of this is a matrix. This whole of this we can call as one matrix, and if we call it and represent it by alpha, we can say that this matrix alpha is equal to whole of this, which is phi omega r square minus omega r square I inverse phi transpose. And this matrix is called frequency response function matrix because it connects forces, physical forces, with the physical response. What is the input force vector? What does it represent? It represents the input forces acting on the system. X, vector X, represents the vector of physical responses, the output of the system. And the relationship between input and output, okay, is quantified by frequency response function matrix. Okay, the relationship between between the forces at all degrees of freedom and the displacement at all degrees of freedom. This relationship is quantified and characterized by a matrix called as frequency response function matrix, and it is related to eigenvalues and eigenvectors through this relationship. So that is the very important learning here, that frequency response function matrix connects input forces with the output displacement, and frequency response function matrix can be expressed in terms of eigenvalues and eigenvectors, or natural frequency and mode shapes of the structure, and of course the omega, which is the excitation frequency. At what frequency you are exciting the system? What is the frequency of the force or the inputs which you are applying? If the frequency of those forces is omega, then the frequency response function matrix is given by this, in which the constant quantities are eigenvector matrix and eigenvalue matrix. That's a constant, while omega is a variable here. Okay. And if you take a 2 degree of freedom system, and then to give you some insight, I have just written down here the independent, the individual matrices here. You can see this is the eigenvector matrix here. This eigenvalue matrix. If you multiply all of this, you get this term here, FRF matrix, and this is the first term of the FRF matrix. So it is for 2 degree of freedom system, you have got a 2 by 2 FRF matrix. Okay. Let us go to next slide. So if I have an n degree of freedom system, if I write down only one of those terms here in the FRF matrix, alpha ij, so alpha ij is basically written like this. From a 2 degree of freedom system, we can extrapolate and generalize it for a n degree of freedom system. And you see on the right hand side, I have got what quantities? I have got ith and jth element. For example, if I can write it in the summation form, so I have summation of these such terms from 1 to n. N is the degree of freedom of the system, and each term here represents response of particular mode of vibration, right? So rth mode, this term tells you the response of the rth mode of vibration and how much it contributes to the frequency response function related to the coordinates I and j, right? So therefore, this is a very, very important relationship for modal testing. So therefore, if you look at the FRF matrix of a multi-degree freedom system, we can represent it in this form. The FRF matrix, alpha 11, alpha 12 up to alpha 1n, alpha 21, alpha 22, alpha 2n, alpha n1, alpha n2, alpha n. So there are, it's an n degree freedom system. So you have n rows and n columns. So there are n into n, that is n square number of frequency response functions. And what is alpha ij? Alpha ij is fundamentally defined as ratio of the displacement at ith coordinate at frequency omega. Don't forget, it is at a frequency omega, right? So xi omega divided by fj omega. Fj omega is the force applied, harmonic force at frequency omega applied at degree of freedom j. And the forces at all other degrees of freedom other than j, they are 0. So it means you are applying only force at j3 degree of freedom at frequency omega, and then you are measuring the response at either degree of freedom, okay, or you are having the response at degree of freedom at that frequency, and the ratio of these two quantities is frequency response function between the coordinate I and coordinate j. Okay. So therefore, in modal testing, what do? In modal testing, we try to measure the response model. What is response model? Response model is description of a system in terms of frequency response functions. Okay, so that is an alternative description. Okay, and that's an equivalent description. So theoretically, there is a one-to-one relationship between the response model and the modal model. Modal model is related to spatial model. So it means all these three models are interrelated and they are equivalent. Okay, they are equivalent in the sense that if you have one model with you, you can go to the other model. You can get the other two models, any one model. If you have response model, you can obtain the spatial model and the modal model. But of course, I would just say a word of caution here that theoretically this is completely possible, but experimentally there are issues. You can have response model, but you cannot get spatial model from that response model because of the incompleteness of the data. Data is not complete. That's the problem. But then the point is that if you have the response model, which is the mathematical description of a structure in terms of FRFs, then it is possible to find modal from this model, which means we can find natural frequency, mode shapes, and damping factors. Why? Because we just saw that there is a mathematical relationship between the FRFs and the eigenvalues, eigenvectors, and damping factors. There is a relationship. So if I can measure FRFs, I can through some mathematical regression, I can find natural frequency, mode shapes, and damping factors. This is the fundamental basis of modal testing. Okay, this is the fundamental basis. So therefore, you can see a system, is described in terms of frequency response function, alpha omega. So it is basically alpha ij omega. So alpha ij omega is a characteristics of the system. Now, if you apply some force on the system, a dynamic force F, and if the dynamic response is X, right, then I can determine from the knowledge of the input and from the knowledge of the output, I can determine what is the system. This is the crux of modal testing. You are measuring what is the force you are applying on the structure. You are measuring what is the response that it causes. And from the knowledge of these two pieces of information, from the input and output, you are trying to determine what is the system to which the force was applied and which is causing the response. So this is basically a black box. You can think of system as a black box. Okay. And then you are giving something, you are putting something into the black box, something is coming out. And if both these informations are given to you, the input and output, then you are trying to answer what is inside the black box, what lies inside the black box. This is basically this is basically what we are trying to do in modal testing. And in electrical engineering, this process is called system identification. Okay, in electrical engineering also this problem is there, that they may have an electrical system, right? And then they want to know what is the model of this electrical system. So similar approach is used, right? That they give some input, let us say voltage input, they measure what is the response, and from these two pieces of information, from input and output, they try to figure out what is this electrical system. And of course, the parameters, there are electrical parameters. But in this particular structural case, mechanical system, our interest is to determine the mechanical parameters or the mechanical characteristics, dynamic characteristics of the system. input-output system model. This is a classic, problem in system identification. We are trying to identify what is the system from the knowledge of input and output. So this is a typical setup, we use for model testing, right? So this F structure we have very widely used in our laboratory classes, for studying model testing and teaching model testing. So you can see here what we do is that, as I told you, we have to measure and input and output. So we must measure input and output, and then we can identify the system, right? So you can see we use an impact hammer. Impact hammer is a instrument or a device by which you can apply force on the system, and you can also measure that force, the force you applied. If you use a normal hammer, yes, you can apply force using a normal hammer, but then you would not know what force you applied. This impact hammer is an instrumented hammer, right? It has got a force transducer at its tip, right? And then there are wires that would run through the body of the hammer, and then at the end you will get the electrical, signal proportional to the force that is applied. So we measure this force, and then this structure would then undergo vibration. So we measure this using an accelerometer. So accelerometer, what does it do? It measures the acceleration at that point, and it gives you an electrical output proportional to the acceleration. So few decades back, we only had charge types of accelerometers, right? Whose output was in terms of charge. They used to give charge output proportional to the acceleration, and then that charge was to be amplified using a charge amplifier, and then we used to get a voltage signal, and then that is result. And the same thing was true with the impact hammer output. But now we have what are called as ICP type accelerometers, an ICP type of hammer, right? These ICP types of hammers and accelerometers, they have inbuilt, charge amplifier. It's a small chip of electronic circuit, right? And that is mounted inside the accelerometer. So you directly get output in terms of the voltage signal, and then you don't any longer require charge amplifier in those applications. But still, we may need charge amplifier under some situations, right? Especially when temperature is high. Okay, so therefore we use an FFT analyzer to acquire the voltage signal, proportional to the force, and voltage signal proportional to the acceleration. And these two signals are acquired through a dual channel FFT analyzer. And then through dual channel FFT analyzer, we can then compute the ratio of Fourier transform of the response signal and the force signal, right? So this is basically the impact hammer. Several impact hammers are available commercially, and so if there is a larger structure, you require a bigger hammer. If a very small structure is there, you require a smaller hammer, right? This is basically impact hammer. So you can see here, we have a force transducer here, right? You can, for example, here you can see a force transducer here, and there is a at the terminal end there is a tip. You can see red color tip. It's a soft tip, metal. So there are different tips that are used, which can be changed. Whatever tip is required. There are three types of typical tips that are provided by the manufacturer: a rubber tip, a plastic tip, and a metal tip. And we can then unscrew this tip and then put the other one, right? And then there is a force transducer here. This is the and then this is the output here you get. Okay. Similarly, you have the accelerometers, right? Accelerometer is a piezoelectric type of accelerometer. And so it gives you a piezoelectric crystal. Basically, it has a property that when it is subjected to strain, then it generates charge, right? So that is the property of the piezoelectric material, and that is used here to build accelerometers. So therefore, let us now perform model test on a cantilever beam, right? So I have simulated this just to show that how model testing is performed. So you can see there is a cantilever beam, and now let us say, for sake of simplicity and explanation, we have taken only 3 points on this. Although 3 points may not be enough to capture higher mode shapes, but let us say we have taken only 3 points for sake of description. 1, 2, 3. So at 3 points, we would like to measure that if we apply force at, let us say, at a point in the translational direction, what is the acceleration at any other point in the translational direction, right? So our interest lies in measuring the transverse displacement and acceleration. Okay. So once this, so what we get two signals, time domain signals, right? One is the force signal f of t, and other is the acceleration signal. Although I have represented here through displacement, but you may get you will get acceleration through an accelerometer. And these time domain signals, then they are captured in FFT analyzer, and then there is a inbuilt routine to calculate frequency response function. And how that is calculated? The FFT analyzer will first of all calculate the Fourier transform of the acceleration signal or the displacement signal. And this is the definition of the Fourier transform, right? So we go from time domain to frequency domain. So I think you know what is frequency domain. We describe a signal in terms of the summation of different harmonic components, right? And then the magnitude and the phase of harmonic components we plot as a function of frequency. That is nothing but the Fourier spectrum. And then we also do a Fourier transform of the force signal like this. And then we take ratio of the two, right? The displacement or the acceleration Fourier transform divided by the force Fourier transform. And this ratio is nothing but the frequency response function, right? So this is how we calculate for a transient acceleration force. A hammer, what does it do? It applies a momentary impulse. So that is nothing but a transient force, a force which is there for a short duration of time, right? So that is a transient force. And therefore, for transient force, we can use these relationships to find the Fourier to find the frequency response function. Now, what we do is that using this definition, now we will calculate the Fourier frequency response function, right? And see that what data is required for performing modal testing, right? So let us see. So what we are doing is we have mounted our accelerometer here at test point 1, and then we are applying force at test point 3. So we get force F3 and response x1 double dot. X1 double dot is the acceleration, transverse acceleration at point 1, right? So if we do that, so the first thing is that the force, you can see what are the force we are applying. If you plot this force on the with respect to time, right, what do you see? We see a big peak here, right? So this represents the impulsive force that is being applied, right? So the force rapidly increases to a large value and then rapidly drops as soon as the hammer is withdrawn, right? So we see an impulsive force, and then what we do, we also capture the acceleration, and that acceleration response will be a decaying signal because the cantilever will vibrate, and because cantilever has damping. So because of that, what is going to happen? The energy that was given initially by the hammer, because of the impact of the hammer, the cantilever was given energy, and no longer more energy is given. So there is some fixed amount of energy given, and that energy will gradually dissipate. And because of that, the amplitude of the displacement and acceleration will gradually reduce because energy is getting dissipated from the system. And when the complete energy is dissipated, the response will become zero, like this. Now what we do is that now we do a Fourier transform of this. You can see this is the Fourier transform. The symbol for the F is this F is the Fourier transform. So when we do Fourier transform, we get, so what I've shown here is the magnitude of the FFT of the force as a function of frequency, right? And what we see is that this is the magnitude. So you can see magnitude is maximum here, and then it is reducing. This is the typical characteristics of the FFT or the Fourier transform of a impulsive force or impulsive signal, right? This is the signal, it reduces. Then we also do a Fourier transform of the acceleration signal, right? So, and then we get this spectrum of the acceleration, and it is showing that, okay, acceleration is very large at this frequency, again large at this frequency, very small at this frequency, and so on. So this is the spectrum, the magnitude of the spectrum of the acceleration, or the magnitude of the Fourier transform of the acceleration signal. The next thing is that now we need to find the acceleration frequency response function, right? Inertance, it is called in the language of modal testing, inertance. Inertance is the frequency response function based on the acceleration. And I have represented here by A13. So what does it say? Response at node number 1 or the test point 1 when the force was applied at test point 3. So A13, right? And this is what we get. It is the magnitude of this A13 being shown on the y-axis as a function of frequency. And this is nothing but the frequency response function. So what this A13 does, it basically is characterizing the system behavior between test point 1 and test point 3, right? Or to be specific, between the translational degree of freedom at node 3 and the translational displacement at node number 1. So this A13 characterizes system behavior, the behavior of the cantilever between these two degrees of freedom. And it's a complete system description. Okay, it's basically the description of the system. Now what we do? Now because we want to know, we will have to get information on all the 3 points. So what we do is now we change our point of application of force to the other point. Now we are applying it very close to 1, which we can say, okay, almost at 1 you can say, although because accelerometer is mounted at 1, physically it will not be possible to exactly apply a force at that point. So practically speaking, what we do, we apply force just next to the accelerometer, assuming that, okay, that point is more or less same as that same point, 1. And then, so what happens? When we do that, through the same process, we get this frequency response function. Now, I have shown here the frequency response function alpha 1, 1. You can see FRF 1, 1, right? The top graph is the magnitude of the FRF, and the lower graph is the phase of the FRF. And this phase graph tells you what is the phase difference between the acceleration signal and the force signal. So it's a relative phase between the X and F, and that is also very important. Then what we do next, we do apply the force at point number 2, and we repeat this process, and that gives us another FRF. And this time the FRF will be designated as alpha 12 or A12, which means the response at point 1 when the force was applied at point 2. This was response at point 1 when the force was applied at point 1. And then the alpha 1, I think there is some this has moved the number A1, it has got disturbed, and this gives us basically A13, right? Okay, this gives A13. So you can see here, in this way we have got these 3 FRFs, correct? Let us go to next slide. So in fact, if I now change the position of the accelerometer, so on the previous slide the accelerometer position was fixed at point number 1, but let us say if I move the accelerometer position to point number 2, then what will happen? I will get these 3 FRFs. When accelerometer was at position 1, we already saw that how we got alpha 11, alpha 12, and alpha 13, these 3 FRFs. At position 2 of the accelerometer, we'll get these 3. And then if we move the accelerometer position to point 3, then we'll get these 3 FRFs, which is alpha 31 or A31, A32, and A33. That is what we would get, right? So in this way, by all the positions, by having the FRF measurement at all the accelerometer positions with force applied at all the positions, we have measured the complete FRF matrix with respect to those 3 degrees of freedom, right? Only 3 translational degrees of freedom. Remember that we have not taken other degrees of freedom, right? So because we are interested in knowing the system behavior with respect to translational coordinates, and that's why we have done that. So we have measured now all the 3 by 3 FRF matrix. So, but then, it can be shown that we don't require this complete FRF matrix. We don't need to measure this full FRF matrix. We need to measure either only one row, like first row, second row, or third row, or first column, second column, or third column. We need only one of these quantities in order to determine model from these FRFs, right? So therefore, in practice, what we do, we will measure only either one row or one column. One measurement of one row, what does it mean? Measurement of one row, if I go back to previous slides, you can see if I want to measure first row, then it means I can fix the accelerometer position at node number 1 and then move the hammer from position 1 to position 2 and position 3 and then measure FRF each time, right? And then the other way is that if I measure one column, what I would need the accelerometer position to be changed each time from position 1 to position 2 to position 3, keeping the hammer position same one. So when hammer is used for applying forces, then it is easier to move hammer position. We can easily change the position of the application of location of the force because we have to just move over to a different place. That's all. But changing the position of accelerometer is little difficult because we have to unmount the accelerometer, again mount it, and mounting may require either gluing the accelerometer or having some thread, small hole created, and then use a stud to mount the accelerometer. So generally glue mounting is preferred because we don't want to damage the surface. But in some structures where we want accurate data, we may have to make a small arrangement to mount a stud there. So therefore, we generally try to go for a roving hammer test. Roving hammer means we row the position of the hammer, and we keep the accelerometer position fixed in hammer testing, right? So we do a roving hammer test in for FRF measurement. Now, what is the influence of hammer tip? If I use a different stiffness of the tip, you see this is the Fourier transform. This is force applied by hammer. This is the Fourier transform. So you can see the energy is the energy in the force is concentrated in the lower frequency range. As frequency increases, the concentration of energy reduces. So in fact, if I this is the expression, and then if I take the response, you can see this is the FRF. So if I use this kind of force and measure the FRF, you can see the FRF something like this in this higher frequency range. Sorry, I'll just have some water. So you can see it is not good enough in the higher range, though in the lower frequency range this is a good FRF. So the hammer comes with different tips, and I'm trying to show you in this slide that what is the effect of hammer tip on the FRF measured. So if I take the Fourier transform of these impulses generated by 3 different tips, this green one is the metallic tip, blue one is the plastic tip, and a red one is the rubber tip. So we see that the rubber tip, the red one, its Fourier spectrum is something like this. So the energy reduces very fast as we go from lower to higher range. In blue, the width of the spectrum is little bit higher, while for the green, it is maximum as compared to the other two, right? So what happens is that stiffer the tip, larger is the frequency range you can excite. Softer the tip, smaller is the frequency range you can excite. Why? Because if I use a rubber tip, say the red one, then after, let us say in this particular case which is shown, after say 6 or 7 hertz, you don't have much energy in the force, so you cannot excite the structure in that frequency range. But if I look at the green one has got a good amount of energy, almost up to 50 hertz, right? Almost up to 50 hertz is a good amount of energy, and therefore I can impart the structure energy from 0 to 50 hertz. However, with red one, I cannot excite the structure beyond 6 or 7 hertz, right? And that's why, depending upon the frequency range I want to excite and the range in which my interest lies in studying the dynamics of the structure, I must use an appropriate tip for excitation. So other method to excite or perform measurement, is using shaker excitation. So this is the setup, using shaker excitation. So you can see here, again, I have the same cantilever and then the accelerometer here, but now no longer we have the hammer being used here. We are using a vibration shaker, or what is called as a vibration exciter. It's basically, often we use an electromagnetic exciter, and in the picture what is shown is an electromagnetic exciter. Electromagnetic exciter works on the principle of Faraday's laws of electromagnetic induction, and because of which, when we there is some noise.
Yes. Hello. Yeah, now it is fine, sir.
Yeah. Okay. So electromagnetic exciter, what does it do? It has got a coil, it has got a core, iron core there, and then soft iron core, and then on that the coils are wound, and that is placed in the magnetic field. And then when we supply alternating current to that coil, the coil is subject, because it is placed in the magnetic field, it experiences a force called Lorentz force, right? That Lorentz force is again alternating force because the current is alternating, and therefore that Lorentz force, what does it do? It excites that coil. And that coil is supported on a soft suspension here, and then that coil vibrates. So then we connect a thin iron rod or a stinger, what is called a metallic rod, or maybe plastic rod. It depends. The material may be different. That coil is connected to the structure. So what happens when that coil vibrates through that thin rod? The structure is also subjected to a oscillatory force, and that is how the harmonic force is applied on the structure through vibration exciter. So the vibration exciter requires a power amplifier to drive it, right? And power amplifier basically performs the job of supplying enough power, okay, to the exciter. Signal generator has the job of controlling the kind of signal by which the exciter will be basically supplied the power, right? So a signal generator allows you to decide the frequency content of the force that is being applied. So if you want a harmonic force, you use a harmonic signal, a sine signal here. But if you want to use, let us say, random force you want to apply, you should use a random signal in the signal generator to apply the force. And then because signal generator can supply little power, it has got a limited voltage range and a power range, and that is why that signal is amplified and then subsequently fed to the exciter, so that sufficient amount of power can be applied to the structure, right? So then what do? Because our interest lies in also the force that is being applied, so we mount a force transducer here, right? So and then we measure the force that is being applied on the structure, right? So in this way you can see, again, we measure the force being applied and then we measure the response that is being generated. Because often we use a random excitation force here, because random excitation force can excite a very large frequency range. And then the frequency response function, therefore, is defined, first of all, by calculating an autocorrelation function, and then defining what is called as autospectral density, which is the Fourier transform of the autocorrelation function, right? And then, similarly, we determine because, we have got two signals here. One is the force signal and one is the response signal. So we need to first of all find autocorrelation between the response signal, correlation of response with itself, that is called autocorrelation, and the correlation of the response with the force is called cross correlation. So we also calculate cross correlation, and then the Fourier transform of the cross correlation signal is nothing but the cross spectral density, and then the ratio of the autocorrelation spectral density or the autospectral density and the cross spectral density. That ratio is nothing but the frequency response function. So this is basically the idea behind finding the Fourier the frequency response function using a random signal. So therefore, using exciter, using signal generator, we can generate a random signal, and then we can feed it to the exciter, and then the exciter will apply random force on the structure. The response also will be random. But then you may think that, oh, random response is there, then how do I get frequency response function? The point is that the random force and response, they basically again are affected by the system characteristics, right? And therefore the response contains information about the way the system modifies the force, and that's why the information about frequency response function is hidden in the spectrum, the random output. Right, and then through this relationship we get the frequency response function. So what do? Let us again go through the simulated process of FRF measurement through random excitation. So what we do is that we apply random force. You can see this is the force versus time, F2t applied by the exchequer. This is the response versus time. This is the random acceleration we are getting, and then we perform FFT. We find the FFT of this force and and the acceleration also, and through FFT, then we determine the autospectral density. So this is the SXX, which is the autospectral density between the X and X signal, right? It is obtained using the averaging the FFT of the response signal, right? And multiplying it by its complex conjugate and then averaging it, dividing it by the number of records. So we have to take large number of averages. So you can see here, the FFT of this, you can see a lot of noise kind of thing here, right? Therefore, we need to take large number of averages here. Okay, this n is the number of averages we take. So similarly, using the FFT of the response and FFT of the force, we find the cross spectral density SXF. And once we do that, then when we take the ratio, you can see this is the FRF we are getting. So this has been obtained by after taking a large number of averages, although these two pictures are based on instantaneous FFTs, but we need to take large number of such measurements and then sum them up and take average. That gives us the FFT, and you can see at some places we have the noise here, right? So now, higher the number of averages, higher we get, better is the estimate of the frequency response function. So in this way, you can see we have got the same, and of course, ideally we should get the same FRF as we got from the hammer testing. So these are the two alternative methods of measuring the FRFs. You may wonder that why we need these two methods, why we cannot use hammer in all the places, because there are some structures which cannot be excited sufficiently using hammer, right? For example, think of an aeroplane structure. right? So it is very common, model testing is widely used in aircraft industry to validate the models, and then we'll see some slides later on that. So therefore, no, aircraft is pretty big, so you cannot, if you want to hit with hammer, you need to apply large amount of force. And if you apply a large amount of force, it may damage the structure locally because you are hitting it with a large force. And also large force is required because structure is big. Number one. Number two, if you are applying at some point, let us say on the fuselage, and then trying to measure acceleration on the, let us say, wings, then maybe that on wing you may not get any signal because the force you are applying is small. It may not be enough to excite the whole body of the aircraft sufficiently, and then you may almost get nothing, and the signal to noise ratio may be very poor because what you are measuring is some electrical noise that might be coming out. The amount of signal is very small. So that is the problem, and that's why you for bigger and larger structures you require exciters, and not just one of them. You may require several of them, in fact. So once you acquire the frequency response function, what is next? Now we do mathematical regression using the relationship between the frequency response functions and the model. And these mathematical regression procedures are often called as curve fitting methods in model analysis. This is nothing but a curve fitting method is nothing but a mathematical procedure of extracting the modal parameters or model from the information of the frequency response functions. And then there are different types of methods like single degree of freedom method, multi degree of freedom method, frequency domain method, time domain method. For example, if I take an inverse Fourier transform of the frequency response functions, I get impulse response function. Impulse response function is another mathematical model of the structure, but that is in the time domain. Okay, so you can either have methods which perform curve fitting on FRFs, or you can also, there are methods which perform curve fitting on the time domain impulse response function, right, which is nothing but impulse response. And those methods are called time domain methods. And then there are SIMO methods called single input, multiple output methods. And they are also called multiple input, multiple output methods, which are used in aircraft industry, IMO methods, because structures are pretty large. So so the output of the curve fitting method, what is the input to the curve fitting method? The measured FRFs or IRFs. And what is the output of the curve fitting method? It gives you a model of the structure, which is nothing but the collection of natural frequency, mode shapes, and damping factors for the modes that were present in the frequency range of measurement. What is curve fitting? So you can see here, basically, what is a single degree of freedom method? See, red one is the measured FRF, and what we are trying to do is by fitting a expression of the FRF to this data. Let us say for mode number 2, if I fit that expression, then I get this blue line, and when I fit that thing, then I can figure out the natural frequency, mode shape, and damping factor for this second mode, right? So but the point is that, so let me, I think the single degree of freedom method, what do? They assume that around a particular peak in the FRF, the response is contributed only by one mode. That is basically the basis of single degree of freedom method curve fitting. They assume that the response is contributed by only one mode of the structure. But in reality, not only one mode, but all the modes contribute response or the FRF, or make contribution to the FRF at all frequencies. At this frequency also, although the contribution of the mode 2 is maximum, but contribution of mode 1 and mode 3, they are also there, although they may be small. On the right hand side of the figure, you can see I have shown that contribution. This yellow curve is the contribution of the first mode to the frequency response function, and blue line is the contribution of mode number 2, and the green line is the contribution of mode number 3 to the frequency response function. Let us look at the frequency range around mode 2. So what we see is that contribution of mode 2 is very high, it is significant, but that doesn't mean that the mode 1 or mode 3 don't contribute. They are also contributing, although the relative contribution is small. So that is the idea behind the single degree of freedom method. They assume that around the frequency range around mode 2, the contribution of mode 2 is dominant and contribution of mode 1 and mode 3 is negligible. And based on this assumption, they perform curve fitting. And such methods are called single degree of freedom methods. Let us look at one of such methods, right? Which is a peak picking, which is called as peak picking method. It is probably the simplest method in curve fitting on model analysis. But the idea is that so that you get an idea that what this curve fitting is and what do you do and what kind of how the output comes in the form of model, right? So let us take this FRF11 and try to see that how we can do curve fitting using peak picking method. So in peak picking method, the natural frequency is taken as the frequency of the peak in the response, right? So let us say that frequency is F1. So we say that, okay, natural frequency of mode 1 is F1, mode 2 is F2, mode 3 is F3. So we can read that from the x-axis. Then in this way, we get the natural frequencies for these three modes. How do you find modal damping factor or damping factor for all different modes? We use the concept of half power bandwidth. Let us say the frequency of mode 2 is omega. This is the frequency in radian per second. On the previous slide I showed in terms of hertz. That's why that was called as F1, F2, F3. This is the natural frequency radian per second of mode 2. And then we look at this. If I zoom this part, then this is the zoom part of this range around mode 2. And then we determine the half power bandwidth, right? So which means what are the frequencies where the magnitude of the FRF is 3 dB less than the peak magnitude. You can see at the peak frequency at omega r, the magnitude of the FRF is 20 dB and 3 dB down is 70 dB line. Now what are the frequencies at which this line intersects the FRF, right? So you can see these frequencies are omega 1 and omega 2. So these are the frequencies where power is half in absolute terms. And in dB terms, this is equivalent to a 3 dB drop in the power. And that's why we have found these frequencies. That is omega 1, omega 2, right? And then we find the damping factor, or what is called as loss factor in case for structural damping, as eta r is equal to omega 2 minus omega 1 upon eta r. This is nothing but the estimate of the modal damping factor for mode number 2. And in this way, we find the modal damping factors for first, second, and third mode by this technique. So in this way, the damping factors become known. Then how do you find mode shape? For mode shape, let us look at mode number 2. Let us focus our attention on mode number 2, which means we are focusing our attention on the second peak in each of these three FRFs. You can see we are focusing our attention. And now if I go back to that expression for the FRF, you can see this was the expression we derived earlier and here I have included damping terms also, although on that slide we didn't have the damping term there. And now if you focus on the second mode and we assume that the contribution of the mode 1 and mode 3 is negligible, then I can write this expression approximately as in using only the second term here, right? And since I now know the natural frequency, so if I substitute omega is omega 2, right? So this term goes away, and then I substitute here already I have substituted omega is omega 2 here, you can see here, and then I can because I know the left hand side, the FRF, I know the denominator, now the numerator becomes known to me. From here then I can find out numerator 512, right? Similarly, I can extend this procedure to the other FRF. So from here, this numerator in this case is 512 into 522. So I get 522 here from here because 512 is already known from here. Then for the third FRF, A13, in the numerator I have 512 and 532. And then because I already know 532 from here, I can find out 512 from here, right? I know 512 here, so I can find 532 from here, which is this one. So in this way, I have found 512, 522 and 532, which together make up the second mode shape, right? Second mode shape is made up of 512, 522 and 532, right? So in this way, I do it for first mode, right? And then I repeat this procedure for the third mode, right? So in this way, the full model becomes known to me. Okay, so I think it's 11:27. Maybe some more time will spend and then we'll stop. In multi-degree of freedom methods, what we do is that instead of fitting one mode at a time, we feed multiple modes at a time. And therefore, these methods are supposed to give you a more accurate estimate of the model because that is the reality. because all modes are contributing at all frequencies. So assuming a single degree of freedom, contribution is not an is not a correct assumption, and that is why multi-degree of freedom methods can give you better, estimates. But they are, obviously mathematically more, computationally and mathematically they are more complicated. So, you can see once for a plate structure, for example, we may get our, mode shapes in this form. We can get the natural first mode of the plate as 67 Hertz, a typical plate, and then this is the response. So I think it's not working. And then the second mode at 137 Hertz and so on. So, and then we will also damping factors from this. So you can see these are identified experimentally, not from using a numerical model, right, or any mathematical model. We have found it from experiment. So that is basically the output of the model analysis. So in this way, the model testing has permitted us to find independently, experimentally, the natural frequency, mode shapes, and damping factors. Now, what are the applications of model testing? Right? Let us spend some time to understand what are the applications. So one of the most important application of model testing, apart from having a experimental estimate of the natural frequency, mode shapes, and damping factors, apart from that, because that knowledge itself you can use to avoid resonances, right? That is one clear-cut application. We can use that data for troubleshooting. For example, structure has a lot of vibration, and through model testing, if we come to know what are the frequencies, then what we can do, we can also know, okay, what are the, let us say if there are some, motors or some, machines which are mounted on the structure, then we can determine what are the operating frequencies of those, equipment. And then we can see, are those frequencies coinciding with any of the, natural frequencies which we identified to model testing. So in this way, model testing can help us to figure out, are there any problems being faced by the current, we can try to diagnose the root cause of the vibration by the, knowledge we get from model testing, isn't it? So that is one application of, model test results to perform diagnosis of noise and vibration problems, right? We can do a diagnosis or troubleshooting of noise and vibration problems using model testing data. The second important application of the model testing is to validate numerical models, because if the advantage of a numerical model is that we can do answer a lot of questions without doing the experiment, because experiments and model testing, it may be a costly affair. It requires instruments, it requires expertise, it requires time, so you need to invest on it. But making a model and using it is a much is economical as compared to doing a model test. So that is why our emphasis would be to have a good model. If you have a good model, then that's good. That we would like to prefer. But then, as I discussed earlier, the question would be how good this model is, how accurate this model is. And therefore, we need to then compare FE model predictions with model test results, so that we can then say, okay, whether this FE model has sufficient accuracy or not. Can it be used with reliability and confidence or not? Those questions can be answered. So therefore, the first application is that how do you compare FE model predictions with model test results? So one important step is mode pairing, because we have got modes, natural modes from model test, and we also natural modes from FE model. How do you compare these modes? So you can't say that the first FE model mode is same as the first mode in the model test, or second mode from the FE model is same as second model test. They may not have the same ordering. The sequence may be different. There could be several reasons for that, lack of sequence. So the first, therefore, step is what is called as mode pairing, and that is done using modal assurance criteria. We use modal assurance criteria for mode shape pairing, right? And what does it do? Modal assurance criteria is a mathematical, tool or mathematical expression to quantify correlation between experimental and FE model mode shapes, right? Therefore, if we have, let us say, n number of, for example, in this case, I have shown the figure for 7 number of FE model modes and 7 number of experimental modes. So 7 by 7. So I can take one mode from the FE set, and I can take one mode from the experimental set, and I can correlate them and see that how close they are, right? I can find how close they are, right? And that is nothing but the model MAC value for that pair of mode. So if I have 7 modes from FE and 7 modes from experiment, I can have a 7 into 7, 49 number of MAC values. And these 49 values can be expressed in the form of a matrix called MAC matrix, 7 by 7 matrix. And generally this, and then the maximum possible value of this MAC number between 2 modes can be 1, and the minimum value can be 0. If it is 0, means which says that MAC value of 0 says that there is no correlation between the ith mode from the experiment and the jth mode from the analysis or the FE, right? And the value of 1 tells you that they are exactly matching. That's what the MAC correlation says, and that's why MAC is a very powerful tool to correlate modes from the finite element set and the mode from the experimental set coming from the model test results, right? And now you can see if I plot them, they are typically plotted in the form of a 3D bar chart. And what we see from here, the large height of the bars, they indicate that the corresponding modes have a very good correlation. For example, if I say this is the experiment and this is the analytical or the FE, then the first experimental mode is correlating very good with the first analytical mode. But the second experimental mode is not correlating well with the first analytical mode, which is correct, because second mode is different than the first mode. Correct. So in this manner, from this graph, you can figure out which mode from the experiment, which mode from the finite element model corresponds to which mode from the model test result. So that is why, and without this mode pairing, you cannot compare the finite element predictions with the model test results, right? Once this has been done, now you can compare what are the frequencies, how do they compare. Now once the modes are paired, the corresponding natural frequencies can be compared, corresponding damping factors can be compared, right? Now there could be sources of discrepancy between FE model predictions and model test results, like inexact values of metal properties being used in FE model, because there are several modeling approximations and idealizations that might be there in FE model. Like boundary condition is an issue, how to model boundary conditions. In FE model, we may idealize them. There will be some problem of joints, how to model joints. Often in FE model, the joints are modeled in a very simplified way. The geometry is often simplified because the actual geometry may be complicated. So sometimes we may do some idealization there. Damping is a problem because in FE we don't know what damping data is to be used. So that has to come from experiment. And discretization error is another issue in FE model, but that can be easily eliminated by using a very fine mesh of the FE model, right? So that is generally small and negligible. That we can ignore discretization error. But we must be aware that discretization error also is possible if one is not careful in discretizing the FE mesh properly. So that is why the updating of FE models is another important application of model testing results. So here what we try to do, we try to determine the uncertain parameters in the FE model based on model test result, right? We can update those parameters and try to get a better estimate of those parameters. So it is very well established field, and in many industries, validation and updating is a important step in the whole dynamic design cycle, right? It's an important step. And we have our students have done several studies on this application of model testing. For example, we have developed a building block approach to FE model updating, where we are trying to develop a validated model for individual component of a bicycle, of a motor vehicle frame, right? You can see it's a motor vehicle frame, suspension, and this other members, all they were validated separately, and then they were combined, and again the combined assembly of all these components was validated through model test results. This is just another picture of that, how experiment was done. So typically, in model testing, there are two ways you can, test the structure. Either in the fixed boundary condition, we fix the structure, or under free condition. So you can see here, this the motorcycle frame is being tested under the free condition. It has been suspended using elastic bands, and now it is under free condition. And then we also develop a free model, FE model of this frame, and then we do the comparison. This is updating exercise on the on a lathe machine in our workshop. We developed the FE model, we performed measured FRFs on this, and then we did the correlation and validation exercise. This is for a body in white of a car. You can see the car being tested outdoors, right? FE model being made, and again the model test being performed. on rotating structures also we have done studies, right? And the model testing is a very important exercise in the validation and vibration testing of an aircraft. GVT is referred as ground vibration testing. So GVT is a very, very important test in the certification and validation of an aircraft. You can see here the aircraft, it is being model tested, and because aircraft is a pretty big structure, probably only one exciter may not be enough to give sufficient energy. Right, and also often using multiple excitation points, a better estimate of the model can be obtained, which are often called as poly-reference techniques of model testing. Right, so therefore that is one application of model test in the aircraft industry, that they do a ground vibration test. Through ground vibration test, they perform model testing, and then measure and identify the model of the aircraft, and then they validate the finite element model of the aircraft using those results. So that is the first level of testing. But that is the first test done on the ground. But actually, aircraft has to fly, and then there is another level of test that is being done. That is in-flight model testing. That also has to be done. So there is an important phenomenon called aerodynamic flutter. Aerodynamic flutter is unstable oscillations of the aircraft wings. And so what happens? The wings, they oscillate, and then it is seen that the vibration of the wings can become unstable. Unstable means that the vibration level or the amplitude of the aircraft wings may increase with time, with speed, right? So that is instability. So it is seen that at certain speed, the vibration amplitude of the aircraft increases with time, which means the vibration is becoming unstable, and that is dangerous, because then if the vibration is increasing, the wings will then flame, right? That is, and it will cause a catastrophic failure. And the aerodynamic flutter, why does it occur? It occurs is because of the interaction between the structural dynamics of the aircraft, the dynamics of the structure, and the aerodynamic forces. Because when the aircraft flies, it has to. There is a fluid, the airflow, and then the airflow generates aerodynamic forces. So the interaction between the aerodynamics, the fluid flow, and the dynamics of the structure, that causes flutter. Okay, and the flutter, the problem is that it's not just vibration; it's an unstable vibration. Unstable vibration is dangerous. And now model testing is done, right, in flight, to determine what are the safe flying speeds of the aircraft. So you can see this is just a schematic of how in-flight model testing is done. So that is why when before an aircraft can be certified for normal usage, it is subjected to flight testing. So this is the flight testing, and this is done for any aircraft. It may be a civilian aircraft, military aircraft. So because aircraft when it flies, the problem is that it's the damping level of the damping factor of the different modes, that undergoes change. That is the issue, right? And therefore you can see that the forces are applied on the structure for acquiring the vibration data, like in doing model testing, and data is transmitted to the ground station. And then they will do all the analysis and then figure out what is the safe operating speed. Okay. For example, this graph says that what is flutter and what is flutter prediction. You can see here several FRFs, they are overlaid. The responses have been overlaid on each other, and they correspond to different speeds of operation. For example, this V is 15 here. The blue colored graph is for V is equal to 15, right? Correspond V is equal to 40 corresponds to a different speed, higher speed. And what we are seeing here, the FRFs or responses, the peaks are shifting. You can see from it is shifting, right? You can see different peaks, they are shifting. And now if you find damping for each of these peaks, and if you plot those damping factors as a function of speed, you can see from here, damping versus speed, then what we are seeing. For some modes, although it is increasing with time, but for some modes, the damping factor, you can see it is for mode number 2, shown by red line. Damping factor is increasing, and after some speed, damping factor is reducing. This is the problem, because if damping factor is reducing, let us say after this, and then if you continue to fly at a higher and higher speed, what is going to happen? If you extrapolate this graph, you can see here it is already reached at something like at 48 meters per second. The damping factor is becoming 0 for mode number 2. And after that speed, the damping factor will become negative. Negative damping factor basically indicates instability, which means that the vibration level, instead of decaying, they would increase with time, and that causes instability. And therefore, in this manner, we try to determine that what is the safe flying speed of an aircraft. And model testing plays an important role here, right? Because without model testing, we will not be able to figure out what are the damping factors, right? Only through experimental testing we are able to know this. And therefore, flutter prediction is a very important application of model testing in aircraft industry, apart from ground vibration test. So other, so I think we are coming to the end of the lecture. Now we have just a couple of more slides. Other application of model testing, as I told you before, that it provides you an independent mathematical model, right? And because we are performing test on the actual structure, if we take all the precautions and ensure that there are no errors, right, in the testing, then the data we get from this test is very reliable and should be considered to be accurate, because it is actually being done on the actual structure, right? All the boundary conditions, all the characteristics of the structure are taken care of automatically, and therefore this model can directly be used. Model we got from model testing for simulating the response of the structure to forces that might act on the structure in practice. For example, if we have developed a prototype for a say a vehicle like this, then we can perform a model test, like a company can perform model test, right? And what can they do? They can use this model to predict that if vehicle is supposed to move on a rough road, what kind of response would be suffered by this vehicle and the passenger. This can be predicted in advance by sitting in the laboratory of the company without actually running the vehicle. We can do that. This is called response simulation, and that is possible without any numerical model, but a mathematical model derived from model tests. This can be done. We can also assess the effects of structural modifications. For example, if we are interested to know if that vehicle we saw on the previous slide, or in this case, this motor example is shown, that if we modify the structure by adding some spring, dashpot or damper or some mass, then how the dynamics of the structure would alter, isn't it? That's for sure. The dynamics would alter, but then how would it alter? And this model we obtain from model test, we can use that to predict the changes which might occur. And what is the advantage of this? The advantage is that then we can answer some what if questions, that if I want to shift this mode because it is resonating, then what do I have to do? Okay, let us say a particular mode is resonating, and therefore to avoid resonance we would like to, and if the operating frequency cannot be changed, then the only way we can avoid resonance is by shifting the peak itself, the resonant frequency itself. So then we would say, okay, let me add some mass to the structure and see that can I shift this peak. All these questions can be answered, and where to change, how much to change, is the change effective? All these questions can be answered using this model. So that is another important application of structural modification. We have also done our studies in our laboratory. Our students, this is one of the theses which was guided the MTech student, that we studied that can we predict stresses in structures using vibration measurement without using any numerical model. So we measured vibration on this structure. So what was the idea? That if I just measure vibration on this, can I know what is the stress? That was the idea. And then what is the information on the structure that was used? It was in the form of model test. So we perform a model test on the structure, and then based on the model, we tried to predict how much is the stress if it is vibrating. So you can see we performed the model test, and then we applied force using an exciter, and then we measure the response using strain gauges, because we wanted to validate our methodology. What we did, we measure the strain at different points using strain gauges, and then we also predicted the strain and the stresses using our technique based on vibration measurement, and then we got a good correlation. You can see here, this is the estimated state using methodology developed, and this is the measured stress using strain gauges. So this particular thesis, we developed this methodology, and this shows that model testing, can also be used for strain and stress predictions, and this can be useful for, condition monitoring or, monitoring the stress and stress levels in structures. And then the model analysis, as I told in one of the slides earlier, can also be done for acoustic systems. So you can see this is one of the simple acoustic system or a cavity we have, in this laboratory. Our laboratory, this is a rectangular cavity. You can see here, and then we conducted a model test on this also. But remember, this here model test is not on the structure. It is inside the air medium. This air medium also has modes of oscillations, right? And those are the oscillations of the air, okay? Because this air is surrounded by rigid boundaries, so air is making a system in itself, and then it undergoes oscillation. If you let us say you can see here some speakers mounted. So when we play the speaker, the air inside the this box, it is excited, and then it also undergoes oscillation just like any mechanical system. Like a mechanical structural system, it undergoes oscillations. And then we measured responses using microphones throughout this cavity, and then we did a model analysis based on those acoustic responses. And you can see these are the acoustic modes of vibration. So this is the first acoustic mode. It's the longitudinal mode at 131 Hertz, and you can see the air inside it is oscillating in a longitudinal direction. This is the second mode. Here the air, for example, if I go back to this first mode, this green contour, it says that the acoustic pressure is 0 here, while this red one, the blue one says the acoustic pressure maximum on the positive side, the red one is the acoustic pressure on the negative side. Okay, so it is telling you a mode of vibration. So this is a nodal plane. This is a nodal plane, acoustic nodal plane. Here you see there are two nodal planes. There are two green, this planes here, and here acoustic pressure is 0. But red planes tell you the maximum, maximum acoustic pressure on the negative side. The blue one is the maximum acoustic pressure on the positive side. So now you have two nodal planes here. This is the third acoustic mode. Now this is mode in the vertical direction. In this direction, the air is oscillating. You can see, and this is a combined mode. In this, the first longitudinal mode and the transverse mode, they are combining. And this is the mode in the third direction, in the depth of the cavity, like this. So you can see model testing is also used for acoustic model analysis. The model analysis can also done for acoustic systems. Okay. And then we also develop methods for updating of acoustic models and vibroacoustic models. So you can see in this this laboratory cavity, we have the acoustic system, and then we have a plate, a flexible plate. So it makes a vibroacoustic system. This plate can vibrate, and we have the the air medium inside being excited. That is an acoustic system. And then we have developed methods for updating coupled vibroacoustic model of this cavity. Just like structural model updating, we also develop methods for that. And then we can see these are some of the results. You can see we are able to predict the acoustic response. This is before updating, this is after updating. So after updating, you can see the blue line, which is the vibroacoustic prediction inside the cavity using the vibroacoustic FEM model, and red one is the response, the experimentally measured acoustic response to the structural excitations, and then the predictions are better. So you can see the applications of this vibroacoustics is in the cavities of the car, right, in the aircraft, and all transportation equipment. We have passengers sitting inside, and we want that the noise inside should be small. So therefore, we need to have a good vibroacoustic design of this cavity, to reduce the noise. So you can see the model analysis is also done for the acoustics and vibroacoustics problems. So I think in this way we come to the end of this presentation from my side, and I would be very happy to take any questions you may have.
Dear participants, any question? So, dear participants.
Yes, sir.
Yeah,
That's great.
So, good afternoon, sir. Sir, my name is Rahul Somyal. So, I am from NITJ Jalandhar.
Yeah.
Yeah, pursuing, sir, my PhD. So, my area of research is to calculate the experimental model analysis for the microwave welded joints. So while I have performed certain experiments, so while performing those experiments, I have faced few issues regarding the oscillometer. So my question is, what are the choices I have if we have the irregular surface of the specimen, we are unable to mount the oscillometer?
Okay.
So,
Yeah, you can complete your question if you want.
so, sir, this is the question, sir. What are the other choices other than mounting a oscillometer on a flat surface? Let's suppose I have an irregular surface. So, what will be the choices for that?
Okay. So see, irregular surface means, if I understood you correctly, right, it is probably a rough surface. Irregular
Yes,
means
sir.
rough.
Yes, sir. Rough, or you can also say that it might be a pipe of 10 external diameter, so that
Okay.
the surface is not that flat.
Yeah. So I think if you want to use only extremometer itself, you want to use take measurement with extremometer,
Yes, sir.
then the one possibility is that you have to flatten that surface a bit if you want to use glue. Right?
Okay.
You have to, using a file, you can flatten it and make it smooth little bit. Right? If that is permitted, that should be done only if it is permitted, and there are no issues regarding any damage. If that is acceptable, any changes in the structure, it is acceptable. Then that is one possibility. The second possibility is that you can also, if it is irregular and you don't want to file it, then you can drill a hole and tap it, and you can use a strut to mount extremometer.
Okay, sir. Okay.
That is second possibility, but that again is should be used only if drilling and tapping a hole is permitted and damage to the structure is accepted.
Yes, sir.
And the third option is instead you can use a non-contact type measurement transducer.
Okay, sir.
That is like a laser vibrometer, for example. You can use a laser vibrometer, and that's a very reliable and very nice method of because it is non-intrusive. It does not interfere the measurement, because you don't have to mount. It is a non-contact type method, and therefore irregular surface etc. should also not be an issue there. And because it requires a small reflective tape to be pasted, and that can be pasted on the regular surface as well.
Okay, sir. Yes, sir. Sir, my second question is, sir, I am pretty much having curiosity or keen about finding out the metallurgical relation with the damping. So, what will be the approach for that, sir? Yeah, let's suppose if there is a structure of stainless steel having a bigger grain structure, and there is a same material with a finer grain structure.
Okay.
So I just want to study a little more in deep in that. So I just want a suggestion regarding the approach of that. So whether the same method, right now I'm using the Oro software and having an impact FEMMAE and oscillometer, that will be a sufficient study for that, or I need something else?
See, there are different issues here.
Okay, sir.
One is I do not know whether you are interested to study only from a experimental perspective or a theoretical perspective also.
Sir, I am dealing with experimental only, sir.
Experimental.
Yes,
so
sir.
Experimental, as far as measurement technology is concerned, what you said, like the software and the equipment you are referring to, so they should be enough. Of course, I don't know. I hope you have the software to compute damping factors, etc. Also, I believe.
Yes, sir. Yes, sir. Yes, sir.
So, as far as measurement and those facilities are concerned, they are enough.
Okay, sir.
Because ultimately, you want to find damping factor, so
Yes, sir.
you can find out.
Okay, sir. So, sir, there is one more question, sir.
Yeah.
Sir, we have a great example or a reference from a Tacoma narrow bridge. That was a failure.
Yeah.
Yes, sir. So I just want to know, sir, that was the failure because of the aerodynamic, or you can say that the natural frequency of the air coincided with the bridge. So I just want to know, for the present point of view, while we are designing a bridge, how we determine the natural frequency of the air?
Natural frequency of air?
Yes, sir.
No. Natural frequency of air is not relevant there.
Okay, sir.
It is not natural frequency of air. It is the natural frequency of the bridge.
Okay, sir.
And the other frequency which has a role to play is the excitation frequency.
Yes,
not
sir.
the neutral frequency.
Yes, sir.
So the wind loading which might act on a bridge, right? One has to characterize that. What kind of wind loading is there?
Okay, sir.
So one can do some measurements of wind velocity, wind loading, etc. And from that analysis of that data, one can determine what kind of loading and its spectral characteristics exist. And based on that information, then one can ensure that the design is safe.
Okay, sir. Yeah,
Okay.
thank you so much, sir. These are all of my questions.
Good questions. Yeah.
Yeah, thanks.
Yeah. Dr. Ashok, sir? Yeah. Yeah, anyone else?
Yes, sir.
If no, yeah, Sanjay. Sanjay, please.
Good morning, sir.
Good morning.
This is Sanjay Kumar. I am pursuing my PhD from NIT Jalandhar under the guidance of Dr. Pramod sir and Dr. Manoj sir.
Yeah.
So my question is regarding the dynamic or structural vibration or the fatigue calculation during the friction stir manufacturing process. When we are applying a two plate into a regular surface, then the mixing inside the stirrer is little different from the third layer of that mixing. So how can we segregate that mixing of the material into reinforcement on the dynamic mode? And can we represent on a software in a live session also for using any equipment or any attachment for the vertical milling machine?
Okay. So basically, if I just clarify you from your side, that you are saying that that mixing process, how does it affect? You talked about some structural dynamic issue. Can you
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
mixing process and what effect on what? Can you?
On the mixing property of that particular plate, which is on size of 3 mm to 5 mm, during the mixing of the reinforcement with the tool.
Okay. So what basically, if probably what you are trying
I
to
want
say
to
is that.
know any attachment or any software which is available that can give the live data of that particular attachment of the friction stir additive manufacturing. That is the layer by layer definition of any particular plates.
Okay, so basically now what I understand is that you are basically talking about what is the life of that component being used for mixing, isn't it?
Yes, sir. Yes, sir.
Yeah. So and then what I see is that probably you suspect that the mixing cycles, which the load would come, and then how many such load cycles it can sustain, right?
Yes, sir. Yes, sir. Definitely.
So I think there are softwares which can predict fatigue life of structures, right? And there are softwares which can study the fatigue life and durability. Okay, so you may have to make a model, and based on that model, it can predict how many cycles of loading it can sustain. Of course, you have to then define what is the load and all that. So I think there are softwares available. You should look for
that is for the prediction. Can it is any software available which is give the live data of that particular machine or particular surface?
live live data you are talking about?
Yes, sir. I'm talking about live data.
Live data, I think that would come from, I think, software. I doubt whether any software will be able to provide that. Software allows you to model a system and then study a particular physical phenomenon.
Okay, sir. Okay, sir. Thank you. Thank you very much, sir.
You should look for either you should yourself try to take some measurements, or look for other sources of information, or from the people who might have done previous studies. You can approach them for that.
Okay, sir.
Yeah.
Thank you, sir.
A great lecture by Professor Modak sir. I thanks to Professor Modak sir for this lecture, for wonderful lecture to our participants. And now we are planning to giving vote of thanks to Professor Modak sir. Ashok sir, please.
So good afternoon to all. So we are very thankful to Professor S.V. Modal Sir ji he find time to deliver this expert talk on this FDP. So we are very thankful to you, sir, because it is seen that also that you delivered a 2-hour lecture on a model analysis, and the lecture was continuous, and it shows that your dedication towards your work, sir, and it is a learning to all of us also, sir, because what happens most of time, we just take 1-hour lecture and think that we have do a lot of things, but you continuously present their lecture for 2 hours, and it gives really a motivation to all definitely it will give motivation to all the participants, sir. So as a assistant professor from NITJ on behalf of the STC coordinator, on behalf of Dr. Manoj sir also, we are very thankful to you, sir, for your expert talk, sir. We are very thankful to you, sir.
So I think dhanyawad everybody for patient listening to my lecture, and I would like to thank Dr. Ashok Kumar, Dr. Manoj Kumar for inviting me for this talk, and I was very happy to also have a good number of questions from participants, and I hope that those who are interested in the area of dynamics, structural dynamics, vibrations, modal analysis, I think they would gain from this lecture, and it will help them to start studies if they are interested in this direction. And I hope to meet again in the future. Thank you so much.
Thank you, sir. Thank you.
Thank you very much, sir.
Thank you. Thank you.
Yeah, everyone, can you give any feedback? Yeah, please, Sanjay, can you give?
Yes, sir.
2-3% please give the whole feedback of this course.
Sir, good afternoon. In my opinion, this STC is very informative and very keep in the flow of the theme. The FEM is essential for any scholar when we are going to practical exposure. All these sessions have give the practical exposure of that software and the theory aspects as well. All the session, which is including the composite material also, or the session on the Ashok sir, or your lecture, or the Pramod sir lecture, that lecture was very comprised in a manner that started from the beginning. The learner or the researcher who are start in their journey in FEM from the beginning, they can also learn a lot. If they have prior knowledge in this field, they also attain the knowledge for the advanced level of the course. So I thank you all the organizer, our department, mechanical engineer, and behalf of the our student community and research community, we thankful for organizing such type of event. Please continue this type of FDP, STC for in near future to benefit us. Thank you, sir.
Definitely we will keep it. Tarun, can you tell? Mandeep said. Yeah, Tarun.
Good morning, sir.
Yeah, good morning.
Good morning, sir.
Through your camera.
Sir, myself Tarun Kumar, PhD scholar working under Dr. Manoj Kumar, sir, in Mechanical Department of NITJ Jalandhar. Sir, it's a great privilege and honor for me for being collaborated with this FDP, and right from the beginning of the lectures in first day, Professor U.S. Dixit, sir, and second day, Professor Dr. Sachin Singh Gautam, sir, third day, Professor Puneet Mahajan, sir, and coming to the fourth day, Professor Sarath Kumar Pardhan, sir, and fifth day, finally, Professor Subodh Madak, sir. It's a great privilege and honor for me, sir, for being collaborated with this FDP, and moreover, irrespective of the domain, whether it may be nano composites or maybe printed or whatever maybe the applications or thermal or design, whatever it may be, finite element modeling is very essential for strengthening our thesis, especially in research point of view. So on behalf of student community, especially in research PhD scholars community, I'm very, very thankful to you, sir. Once again, it's a privilege and honor for me, sir. Thank you.
Yeah, thank you, Tarun.
So Ashok, can I take a leave now?
Yes, sir. Yes.
Thank you.
Anand has written something, sir.
Acha.
Yeah, just I want to read it. Yes, sir, I am Anand. I am extremely thanks to Dr. Manoj Kumar and team for each and every faculty, speakers, organizer. Thank you, Dr. Anand. Thank you, sir, for coming and giving us time for this, sir. Thank you.
Okay. Bye.
Thank you, sir.
Bye.
Okay, participants. In future, if you have any problem in model analysis and FEM, please try to connect with us. We will try to solve your problem. See, ultimately you have to work it, but our duty is to give you a right path. And you have to run on that path only. Yeah, please, sir. Ashok, sir, please give some points.
Any,
I want to give-
any participant? Yes, Jitendra.
Yeah, Jitendra, if you want to speak, please say something.
Sir, this STC provide the basic knowledge to advanced knowledge, and experts have explained in a very lucid manner, so anyone can understand. Even the normal person can understand what they are trying to explain. And main thing is that they have explained the live problem. They have connect the theoretical problem to the practical problem, and this is the main key concern of the STC. And I feel very privileged to have or to listen from the experienced faculty. I wish this STC will happen in future also, and it will be beneficial for us. Thank you, sir. And I thank you both coordinators, sir.
Yeah, Professor, no, not both coordinator, I should say without helping of each and every faculties from Department of Mechanical Engineering.
Actually,
It will not be successful.
Actually, we are very thankful to the students, our PhD students. Without your help, this STC is not possible.
Yeah.
So we are very thankful to you.
Especially Rahul and Jitendra.
So Rahul and Jitendra are the gems of our department.
Right.
So they always helps us, and other students also. I'm not, if I'm not saying anything.
Professor Sukla is here. Professor Sukla, our former head of department. Yeah, sir.
Dr. Manoj and Dr. Ashok, congratulations to you people for the successful completion of your short-term course
Thank you, sir.
on FEA and model analysis. So I congratulate all the participants who got benefited from the expert talks by the eminent personalities throughout the country. Because one is from IIT Guwahati, another is from IIT Delhi. Then today is also Dr. Modak is from Delhi, and number of other maybe from Rajasthan also, BHU also. So the most important thing is what we people learn from this course, and after that how we can take the legacy of these people in our research work, so that we can improve our research activities. So I congratulate the organizers. On behalf of our department, we extended our full support. So once again, congratulations to all the participants and the organizing team. Thank you, Dr. Manoj and Ashok, for inviting me. Thank you.
Thank you.
Thank you so much.
Dr. Ranjan sir is here and Dr. Srinivas sir is here. Sir.
Yeah, good afternoon to all. It's
Good afternoon, sir.
Good afternoon, sir.
it's congratulations to all the team, and especially Dr. Manoj Kumar and Dr. Ashok Kumar. And really, this finite element analysis is useful to all engineering community, especially the mechanical engineers. And I hope all the participants got the benefit from the eminent speakers of this wonderful 1-week program. Thanks, Dr. Manoj and Dr. Ashok.
Thank you. Thank you so much, sir. Thank you.
Yeah, Dr. Ranjan sir. Yeah, Dr. Rajasekhar.
Dr. Rajasekhar, sir.
I think he has some academic, or that is the reason behind he is not able to write.
Yes.
Rajasekhar, please, sir.
Dr. Rajasekhar, sir.
So, good afternoon, everyone, sir.
Yeah, good afternoon, sir. So your feedback is very, very important for us. So kindly give your feedback, sir. Actually, I was waiting for your feedback.
No, sir. Yeah, no. Thank you so much for giving me an opportunity to give my feedback. Actually, it is not a feedback, I would say, but it's really a wonderful experience for me because I have been waiting for this this workshop. In fact, from so long, from so many months. But finally, I would feel that from the experts who are coming all around premium institutes of India. And definitely, I would say that I am benefited out of this workshop. And of course, I was in CFD field, but using finite volume method. But now I could able to venture myself into finite element analysis also with the even the model analysis that was given a light, and that was really wonderful for me. With the thermal analysis also, how this model analysis, that means thermal load also, how the model analysis can be performed, that was explained yesterday, was really helpful for me, sir. Thank you, Dr. Manoj sir, for giving me this kind of opportunity to speak, and Dr. Ashok sir. Really wonderful, sir, I would say. Thank you very much. I never thought I would be given an opportunity to give me my view, but really wonderful, sir. Very nice. Thank you, sir. Thank you so much.
Thank you so much, sir.
Thank you, sir. And now, anyone else?
Anyone else?
Yeah, anyone else? Tarun Preet Singh.
Tarun Preet.
Yes, good afternoon, sir.
Yeah, good afternoon, Singh. Please say a few words about your experience.
I would only
What is
like
your
to
feedback?
congratulate both of the professors for conducting such an informative course for FEM. It was advantageous both for the students who were beginning with the FEM and who have initially been doing FEM for several structures or civil mechanical structures. And thank you.
Thank you, Singh.
Thank you, Tarun.
Yeah, thank you everyone, and I kindly suggest you to please fill the feedback form for each and every expert, and we will try to send you your certificate. I think end of this this week itself. I will mail you. If anything else, please share with me.
If you want to ask anything or if you want to share anything,
If not,
you can
any question, then we can leave. If not, then everyone, okay, thank you.
And best wishes and happy Holi to all
Happy
of
Holi
you.
to all of you. Okay, sir.
Okay, participants.
Okay, participants, take care.
Take care, please.
Thank you,
Holi,
sir.
Thank you, sir. Thank you very much, sir.
Okay.
Thank you, sir.